Hi, I am making a video on neurosignaling and synaptic transmission, a screencast actually, and it's just explaining a little bit about how synaptic transmission works and how action potentials work. I'm talking about a whole bunch of stuff, um, and then explaining how Novocaine interrupts this process.
When a neuron is in resting potential, there are more sodium ions outside of the membrane and more potassium ions inside. During resting potential, neurons have a negative overall charge, so the neuron is polar. Sodium-potassium pumps open and push in potassium and sodium goes out. This creates an electrochemical gradient, which means there are more positive ions outside of the neuron. Other than the sodium-potassium pump, there are many ion channels to allow molecules to pass through the membrane. A presynaptic neuron is excited by a previous neuron's action potential, which is an electrical signal that travels from the dendrite to the axon terminal. So, the resting neuron is depolarized. The sodium channels open and sodium molecules either enter neurons, which causes the neurons to become positively charged. This is called an all-or-nothing phenomenon that must get up to a charge of negative 55 from a charge of negative 70 to fire. The electrical charge is sent down the neural axon. Myelin sheaths cover the axon and allow the electrical signal to move faster.
Note that the signal does not travel through the axon, but instead travels over the myelin and bounces between the nodes. This is what an axon's ion channels and pumps look like. You can see that the axons have two voltage gates, one for sodium and one for potassium. It also has a sodium-potassium pump. A voltage-gated channel only opens when the ion reaches a specific voltage. Otherwise, it remains closed and the ions cannot go in or out of the axon. The voltage gate for sodium opens at negative 50 volts when the membrane potential reaches negative 50. The potassium opens at 40. This means that neither of the voltage gates are open at the same time. When at rest, the sodium remains outside of the axon and is more positive outside. The more negatively charged proteins are on the inside, which is also where the potassium is. When the membrane potential reaches negative 70, the channel opens and sodium can enter the axon. This is known as depolarization. Following depolarization, the sodium channel closes and the potassium channel opens. This is called hyperpolarization because it drops below 70 when it hyperpolarizes before returning to resting potential. Following hyperpolarization, the potassium channel closes again. Now, however, the sodium and potassium are on the wrong sides, which is why this pump comes into play. This pump allows the sodium to return to the outside and the potassium to the inside of the cell of the axon, preparing it to depolarize again. Following hyperpolarization, the membrane potential returns to rest, ready to fire again.
Then, potassium pumps open to allow potassium ions to flow outside of the membrane to rebalance the charges. This is called repolarization. Vesicles are sacs with neurotransmitters in the presynaptic neuron's axon terminal. The synaptic cleft is an area in between a presynaptic neuron's axon terminal and a presynaptic neuron's dendrites. When action potential reaches the axon terminal, it activates calcium ion pumps, which pump in positive calcium ions. This forces vesicles to fuse with cell membrane, and neurotransmitters are released into the synaptic cleft. During the process, the electrical signal is converted into a chemical signal. Neurotransmitters in the synaptic cleft combine with the receptors of the postsynaptic membrane. Neurotransmitters become either excitatory or inhibitory. An excitatory neurotransmitter causes the neuron to depolarize by making the inside of the neuron positive, putting it closer to its action potential threshold. An inhibitory neurotransmitter hyperpolarizes the neuron, making the neuron more negative, driving it down away from its action potential threshold. After transferring the message, neurotransmitters go through reuptake, where they are absorbed back to synaptic neuron, or they are broken down by enzymes in synaptic cleft.
After the chemical signal has been sent to the next cell's dendrites, the neurotransmitters which are still in the synaptic cleft must be removed. One way to do this is through reuptake, in which the neurotransmitters simply return back into the vesicles. However, there's another way to remove these neurotransmitters, and that's by using a astrocyte, which can vaguely be seen up here. These astroglial cells remove neurotransmitters from the extracellular space, so that not all of them have to undergo reuptake. Typically, neurons work by picking up a sensation of pain and then firing an action potential through the end of a neuron, and then sending that message to the brain. Novocaine interrupts that. That is why Novocaine is considered an inhibitor. This means that Novocaine works by keeping neurons from communicating with each other. This is what normal synaptic transmission would look like. The chemical receptors receive the neurotransmitters and use that to create the action potential which would be sent along the neuron. However, Novocaine blocks these receptors and prevents the neurotransmitters from being received, and therefore preventing the message from being sent. When a neuron receives the message from the first neuron sending the pain signal, it can't open the ion gate, which causes the neuron to fire, therefore preventing the neuron from firing, and therefore the pain signal does not get sent and doesn't reach the brain.